So like I said just now, this is going to be a repeat of the key ideas that were introduced yesterday, so that in the grand scheme of things you will understand why you are solving certain problems. So you will see the solutions to those problems later on in the second half of the session. So in this first 30 minutes we just recap what we did yesterday. How many of you know Backstreet Boys, the band? Yes? No? What? Backstreet Boys. Okay. Backstreet Boys.
Backstreet Boys.
Oh, yeah. Right. Do you want to sing along? Yes, no. Anyone interested? Yes. Then we will only listen because I have to make it forward. More than anything, okay, so where I want to can you hear me? better. Hello. Okay. So okay. So too loud. Yeah. So if we wanted to make this, the way I want to think about this is, let's see what we would need if we want to come up with an AI model that would be able to start with the first 10 seconds of the song and generate the rest of it. Okay, I'm going to go through all the ideas that we discussed yesterday, keeping this as our overall broad motive. So, one thing that really sets this song pretty well is the lyrics. The lyrics are like, and they're emotional, and let's see what happens if I just take this lyrics and put them into Gemini. Sorry, not Gemini, Gemma. Okay, so the first idea is, how do I convert something like text, which is a bunch of words, into something that a computer can comprehend? And the idea is that you associate with each word a vector. So vectors pointing in different directions mean different things. For example, if you have to go, so for example, if I put heartache, let's see what words, oh there is, heartache is not there, let's look at what boy is there. So the closest words to boy seems to be girl, boys, man, woman, baby, young, pretty, advanced brother, friend, little kid. Okay, and let's see in this vector space, we have beautiful villain, hamster, Gilbert, Jackie, Charlie. Okay, interesting. Let us just look for some names. Right. So next to Adam, let's see the word that are closest to Adam. And you have a lot of male, like Western male names. You have so you have Friedrich here, you have Richard, Angel, Stephen, Greg, Alan, Robin. The closest words to this is, okay, Adam, closest is Eve, Daniel, Kevin, Matthew, Peter, Abraham, Sarah, and Iman. Okay, so basically there seems to be that different directions mean different things. And if you look at words, again, you want to make some AI model that's able to generate the song. At a minimum, it should be able to take these words and get some meaning out of it, right? So coming back, let's see what happens if I take just one sentence from the song. The chorus, the first line of the chorus. Tell me why you're nothing but a heartache. And let's see, and what I did is I went inside Gemma and I looked at a bunch of directions that Gemma used to, like, work through this sentence. And I took those directions and tried to figure out what they mean. If you want the exact details of how I did this, you can come to me after the session. But the first vector that has a lot of very high similarity, you can say, is the words that are most associated with it is regret, remorse, regret. And also the same vector also gets activated in these sentences. After all these years later, she felt a painful sting in her heart. Okay, and the explanation that like an LLM came up, seeing all these examples in this work, was that this is related to emotional experiences, expressions related to pain and loss. Second, you have references related to trust and relationships. You have discussions of emotional pain and loss. You have expressions of deep emotions and feelings, questions or expressions of curiosity, emotional expressions related to sadness and pain, references to various kind of challenges and obstacles faced in life, themes related to pain and nostalgia, phrases related to causality or reason, and themes of emotional struggle and desire for freedom. So it's pretty crazy that you start from just one line, tell me why nothing but a heartache, and Gemma has read this one sentence and realized that it's associated to some sort of emotional pain, and this person is feeling regretful, like has some regrets, it's related to some relationships, there's some trust that was involved or some bonds that were involved and maybe broken, that are lost, and he's experiencing some voids and he's reminiscing that void, and there is some feelings involved, and this song maybe is evoking those feelings or something's evoking, and he's frustrated and disappointed at the fact that this, and there are a bunch of and all of this is driven by memories, and at the end it's leaving the person writing this disheartened, sad, and bittersweet. So very interesting that from one sentence you were able to pull up all of these concepts. And now if we start from where we started, like I told you are taking a word and I am associating a direction with that word. Ideally then, if I was just doing that, tell me why nothing but heartache, you would only get the vectors associated to tell me why nothing but heartache. How am I getting emotion and relationships and trust and all of those concepts, the vectors corresponding to those concepts with just this one sentence? Any guesses? What could help this happening? Idea is that different words point in different directions. You had one set of words, but now you have words that point in other directions which are also related coming into play.
You will find the most closest vector to that particular word and associated. Whatever sentence that word is, the vector corresponding to you will give the subject.
Okay, you're saying you take related words and based on those related words you see what other concepts are related to these words and then you keep building that way. That is an interesting point. You have something?
That sequence of words matters as
Yeah,
well.
correct.
So we have to come up with a way such that everything is equal.
Exactly. So that's a very good point. Maybe right at the start, at the word level, all that matters is the vector corresponding to tell, the vector corresponding to me, the vector corresponding to y, so on. But when you want to make sense of this as a whole sentence, you have concepts that are related to the sentence as a whole. And all of these ideas and concepts are related to the sentence as a whole. So the transformer in some sense is operating at, I gave away the word, this AI model, Gemma is working at various levels of abstraction. It's working at the words level and at a more sentence level. And how did it extract emotional nuance from just one line?
Attention mechanism.
Huh?
Attention mechanism.
Yeah, and that is where I am going into. The architecture that powers Gemma is one of your LLMs, is something called the transformer. And the transformer has a couple of key parts. One is it takes up words, which we will call tokens, and it converts them into vectors. So embed takes the words and converts them into vectors. So what would happen is, tell me why nothing but heartache, you will get one vector for tell, me, why, end. For each word you get a different vector. Okay, then you have two parts. You have something called the attention and you have something called the energy. So again, if I want to process one word at a sentence level, different words are related to each other in different ways and I want to look at two different words in context to each other, right? For example, if I was playing cricket with a bat and the bat flew above my head, those two, the word bat means different things and I need the capability to distinguish between the bat vector in these two different sentences. So I need to be able to do some transform on the bat vector to be able to do this, okay? That's one set of ideas. Second set of ideas is, as I go more and more abstract, I will want to do some transforms on this vector so that if I have one direction that's related to emotions and I want to take heartache from a medical condition to like an emotional heartache, it's from a medical heartache if that exists, right? So I would also probably want to do some sort of, when I'm doing the similarity across words, I want to do a rotation first and then look for similarity. So again, stepping back for a minute, how would you quantify similarity between two vectors? Any guesses?
Cosine similarity.
Dot product. Cosine similarity, dot product. Everyone knows what a dot product is?
I don't understand why you have to rotate it.
So if you have to build different levels of nuance, if you just take tell and me, you just get one number. But suppose I have to extract different levels of nuance from tell and me, I take tell and me, I rotate or project them into different subspaces and then check the similarity in that subspace. Okay? I mean, this is a post hoc intuitive explanation. There could be a lot more things happening underneath, but this is one way for you guys to make sense of
The meaning of tell and me in a different sentence.
So in this vector space, the vectors are pointing in two different directions. I can project them into a subspace. Maybe that subspace has some meaning, and I'm looking for similarities of these words in that subspace. Okay. So in practice, how would you do that? Again, you mentioned the attention mechanism, and what is this QK is what we are interested in. So this is the projection I was talking about. You take your input vectors and you're projecting into different subspaces and you're checking the similarity of each word in those subspaces. So you're taking the input, multiplying with the query matrix, you're getting a query vector, you're taking the input, multiplying with the key matrix, you're getting a key vector, and you're finding the similarity of the query and key in the particular subspace, and that way you're able to extract different levels of nuance, right? And like you saw in the diagram before, you had your transformer, you had one layer attention, then you had MLP, and this doesn't just happen once, it happens several times. For example, in Gemma it happens 26 times. You have 26 stacks of attention MLP, attention MLP, attention MLP, and so on. So that way you are consistently pulling out certain similarities, adding back into the residuals. So you have the original vectors here. You did some transform. You're adding corrections to the original vector. Again you're doing some transform. Again doing corrections to the original vector, and continuously repeating this process to extract nuance. Right? Okay. So that way, let us go on. And we have to do a lot of this parallelly, different notions of nuance you want to capture at the same time. If you have only one attention head, you can capture only one type of similarity. So what you do is just do it multiple times simultaneously. You have like 8 attention heads all capturing different nuance. But what's wrong with this? The thing is, again, I said the same sentence, tell me why nothing but a heartache, and this is how Gemma is associating attention scores to each of the words. So again, I'll play this animation. So this is actually the attention head number 5 with layer number 24 for each of those tokens. So right now this is tell, what's the first? Oh, beginning of sentence. Beginning of sentence, tell me. So this is a 3 by 3 matrix. When you get y, it's a 4 by 4 matrix. Oh, yes. So 1 by 1, 2 by 2, 3 by 3, 4 by 4, 5 by 5, 6 by 6, 7 by 7, 8 by 8, 9 by 9, 10 by 10, 11 by 11. For a sequence with 11 tokens, we made a 11 by 11 matrix. So that's 121 elements, right? So how does this scale? It scales with the square of the length of the sequence you put it in. And this is gloriously expensive. Because if you took a small text, like a WhatsApp message like 512 tokens, that requires about 200,000, 262,000 elements in your attention matrix, which over entire Gemma, which is like a model with 8 attention heads and 26 layers, requires about 200 MB of RAM. Okay. A long paragraph with 2000 tokens requires about 3 GB of RAM. Short document with 8000 tokens, 55 GB of RAM. And okay, now we are doing one sleight of hand here. I told I wanted to generate the song I wanted that way. I want to send the first 5 seconds and generate the rest of the song, right? So we need to not just take care of the words, we need to take care of the audio part also. And that is a whole other challenge. Have you ever heard of sampling rate? Something you've seen CD players say 48 kHz or 44.1 kHz. Have you seen that somewhere? Okay, so what that basically means is that 1 second of audio is represented by 44,100 points. You have a long array. That array has 44,100 points for just 1 second of audio. Right? So if you have this song is like 220 seconds, so that's 44,100 into 220 floating point numbers to describe this song. Okay, that's crazy. Now what we do is, okay fine, we cannot deal with such fine control. We will do some sort of compression, we will do some very fancy algorithms and say that we need only 50 tokens per second. From 44,000 tokens, from 44,000 floating point, I'll compress it down to 50 tokens per second. Okay. Even if we do that, I still have more than 11,000 tokens for for this song. I want to generate the song was my goal, right? And suppose I do it with another transformer from music, say something like music gen, that has 28 layers, 8 attention heads. So each attention matrix is 121 MB, and I will need a total of 185 GB just for the attention matrices. That is just one part of this attention block. So if you come back here, in this formula, this alone is going to take 185 GB of RAM, right? And that is just one part, and you also have this NLP, and you have unembed and embed, and okay, now you can see that this thing is going to go crazy. And say I actually wanted to come across and train this for
I want to clarify.
Yeah.
You are using the whole audio in the background for the whole line, and
Yeah.
you are giving only the initial ones.
So no, so basically, again, we are modeling a sequence, right? So when I say the 10th word, the 10th word is dependent on the first 9 words that I say. So the 11th word is dependent on the first 10 words. So how I'm going to go about this is I'm going to predict one word. Now I'm going to take the first word and predict the second word. Now to predict the third word, I'm going to take the first word, second word and third word. To predict the fourth word, I'm going to start 1, 2, 3, 4. Now to predict 5, I will again start from 1, go whole pass again and reach 5. Okay, but what I do is I do this in parallel, so that is why you were saying that matrix grow in size, right? So starting with 1 cross 1, 2 cross 2, 3 cross 3, so on. You're doing it in parallel, but you have to do, you're just adding one token at a time, one step at a time. So you have to do 11K, you're going from 1, 2, 3, 4, 5, you're running this thing and you're going to get this 11,000 cross 11,000 dimensional matrix, which is going to take 185 GB VRAM.
So
Yeah.
you're using just the words or some other audio?
Oh, it's going to be like a mixed representation of audio and text.
Audio will be the whole sequence of the song?
Yeah, so I'm doing some fancy compression. Like let's just forget about that. Some fancy compression I do to get audio tokens. It's not words alone. Because I again, my goal was when I started with this, I want to generate this song, right? I want to generate this song. And okay, so now I decide I want to train this. To make this training make sense, I need GPUs, and I probably need to, like, this original model was trained on 20,000 hours of music, and I will need at least 640 GB RAM because that one matrix itself is taking 180 GB, meaning I need some threshold. So 640 GB RAM, that's 1,700 rupees per hour. My song, like my training data is like 20,000 hours of music. And my account balance is 689 rupees. Okay, this is not going to go anywhere. I need something cheaper. I'm going to go broke if I even try this. Okay, so no chance this happening. I can't even run for like 20 minutes. I lose my money before 20 minutes for this. So keep that idea. Transformers work very well, but it's extremely expensive. So we will go aside and start from something which again everyone knows. Everyone knows this, right? Okay, what is the voltage here? It's grounded, that is 0 volts. Right here it is the source voltage Vs. This is the voltage across the capacitor, this is ground, there is current I flowing through, so here it is IR, right? So Vc is equal to Vs minus IR. What is the charge across the capacitor? Q is equal to Cv. I differentiate this, I is equal to C, dVc by dt. I replace this up here, Vc is equal to Vs minus Rc dVc by dt. Okay. Now I just do some manipulations. I get dVc by dt is equal to minus 1 by Rc Vc plus 1 by Rc Vs, right? So far so good. Now what I do is I will just, okay, everyone's familiar? And everyone's familiar? So now you know that this thing is E plus H minus Vc of T whole divided by H, limit H tends to infinity. So, tends to 0. Alright? And suppose I take a scenario where my time step is so small that my signal barely changes. Right? So I'm going to just stick to a discrete scenario right now. I'm going to just go dVc delta minus Vc of t divided by delta. Okay, and now I'm going to put this here and I'm going to just again do some manipulation. Vc of t plus delta is equal to 1 plus 1 minus 1 by delta by Rc. Vc plus delta by Rc Vs. Okay, so now what I do is I discretize it even further. This is like suppose t is equal to k delta and I said delta equal to 1. This is like the Vc at time step k plus 1 is equal to A times Vc at time step k plus B times Vs at time step k. Okay, let's think about the circuit once. What is the input to the circuit? The source voltage, right? The source voltage. The source voltage X. I'm just going to call it Xk. Oh, sorry, no, UK. Okay, I'm going to call my source voltage UK. This is B. What is the state of the system? The state of the system is the charge in the capacitor, right? So I'm going to call that Xk. So this is A Xk, and this is Xk plus 1. So Xk plus 1 is equal to Axk plus B UK. And this is something called this equation is going to come again and again and again and again in today's session. Okay, this is like the key equation for today. Everyone with me so far? I know it's a jarring change to go from songs and GPUs and all of that, and I was like, let's take an AI model that can generate that song, and then I suddenly went to RC circuits, but like let me cook, right? So, right, this is where we are. Now what we want to do is, this is a recurrent relation, right? You see that Xk plus 1 depends on Xk. So I will remove the recurrence. I will just expand this out. So I get Xk plus 1 is equal to A into, this is going to be, can you tell me what Xk is going to be? A times Xk minus 1 plus B times UK minus 1 plus B times UK. So this is what? A square Xk minus 1 plus AB UK minus 1 plus B UK. Okay, and you can do this again and again, and eventually you will get something like this: A power L x0 plus summation I is equal to 0 up to L A power L minus I U. Okay, you're going to get something like this. You can work it out, but for now, trust me on this, just to save time. Right? And suppose we set the input to 0, like the initial state, the charge of the capacitor is 0 at time equal to 0. We basically, so now what we are getting is, you have two sequences. You see, oh, there's a B also. Yeah, you have two sequences here. You have the input sequence, that is the source voltage you're giving at each time step, or now we just remove from voltage and go from to any sequence, and the source voltage at each step, and you have this other sequence which is basically just B, BA square, so on. Okay, these are all right now constants, so it doesn't matter whether I like commute them or not, but in general we will make this as a vector equation, then this will become matrices, then commuting them is matrices don't compute, right? So I can't do all this very scammy kind of calculations right now, but it still is a convolution. I just have to be more careful. Okay. So basically, now you have two sequences. So okay, what I wanted to point out is you have two sequences here. You have one of them which is the input sequence, and the other one which is this sequence: B, AB, A square B, AQB, and so on. And what I want you to notice is that at time step K, when I have UK here, when I have UL here, I have UL minus L. I have this term. Okay? When I have UL minus 1, I have this term. I have UL minus 2, I have this term. So basically, I'm going in opposite order. Do you see that? Right? So it's basically I have one sequence that's going in the forward direction, and the other sequence I have shifted and going in the backward direction. Okay? So that operation is basically something called a convolution. Okay? And so if you look at this animation, you have one sequence here and you have another sequence here. What you're doing is you're taking the first sequence, flipping it, and moving it from minus infinity to infinity, and adding the overlaps. Fine? Everyone's okay? For another example, what we do is also in continuous time, you can look at the same thing. Suppose I have some input, can everyone see the input? And I have some filter, right? It allows very low frequencies in. And suppose I want to convolve these two. Let's call this x of t, let's call this h of t, right? And I want to do x of t convolved with h of t. Now in continuous time, whatever summation I wrote earlier becomes a integral. So this is going to go from minus infinity to infinity. H of tau minus t, x of t, theta. So if you look at this again, it has the same form of whatever we saw just now. We have one sequence that's going in forward direction, the other sequence we have flipped, right? It's coming minus t, and we have a tau here. And the tau is moving from minus infinity to infinity, right? Integral limits are from minus infinity to plus infinity. So let's do this. Let us take this signal, flip it. So if you flip it, you're going to get something like this, right? And you're going to move the signal from minus infinity to plus infinity. So what I'm going to do is I have the signal, right? I go from minus infinity to plus infinity. Right now I multiply these two, there is zero overlap, I get 0, right? Then I come here, I get some overlap, I just get this much region overlap. This is what an area under the curve, right? So I get this area, and whatever that area is, I say that is the point here. I move a little bit front, I get this much overlap, and I get that much overlap. I find the area here, and then I move a little bit more front. I get this. I get sections between here and here that are overlapping, and I find the area under that, and because that I get some other term. Okay, that is the convolution operation. And what your RC filter, the RC circuit does is exactly that. It is a low pass filter. Whatever operation I did here is exactly what your RC circuit does. How many of you know what a low pass circuit is? Low pass filter is? Yes? No? Okay. For a very practical example. Hello? 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 What is the difference? The first time I shut off all the bass and put only the high frequencies, so that was a high pass. It let only the higher frequencies in my voice pass through. Yeah, I'll set it back to normal. And the second time I cut off the high frequencies and I cut off the high frequencies and let only the low frequencies go through. So that's a low pass filter. A low pass filter allows only low frequencies to go through. A high pass filter allows only high frequencies to go through, and your RC circuit is an example of a low pass filter. In fact, what is happening inside that box, inside the mixer, is like a fancy, very fancy version of this with a bunch of other components, but okay, for now, it's an RC circuit. One very important point here is that NPI system, you see, this is an example of an NPI system. It is linear. Okay, fine. LTI means linear and time invariant. Okay, so if your capacitor is initially uncharged and your this capacitor and resistor values you cannot change, so if you provide a time step, if you provide a voltage at time t, or you provide, if I provide an input today or if I provide an input tomorrow, my circuit is going to behave the same. It's going to be a low pass filter. Today, tomorrow, day after, till the end of time. It's just going to be a low pass filter. Right? That is one. So it's time invariant. And second thing, it is linear. In the sense that if I provide one voltage source V1 and I provide another voltage source V2 and I add them up, then what I'm going to get is a low pass on V1 plus V2. It's not going to be some other fancy thing. If this seems obvious to you, this is not true for all functions. If you just have x1 plus x2 squared, you get cross terms. But if you have a linear function, you don't get cross terms, and that's the point. And this is a circuit where I can give V1 here and I can give V2 here, and the output is whatever I would expect for V1 plus V2. Okay? And no funny terms other than that. And your RC circuit is a low pass filter and is an LTI system, and because of how I derived this, this is also an LTI system. Okay? It's an LTI equation. And LTI equations have one issue. They cannot change the frequency content. What do I mean by this? You saw what I did just now. I can increase the bass in my voice and I can remove the high frequencies. I can remove the high frequencies and I can increase the bass, or I can put it back. But I cannot add frequencies to my voice that aren't already present in my voice. Okay? If I have 100 Hz in my voice, I can modulate the magnitude of 100 Hz. But if I don't have 200 Hz in my voice, I cannot add 200 Hz. Fine? That is a property of LTI systems. And now specifically, but I want it that way, and I want to be able to add frequencies to my voice, and this is specifically why I took that song, because if you look at the first chorus, okay, and if you look at the last chorus, last chorus, do you hear that? It was like, and this is higher, right? Did everyone catch that? There is this song uses something in music called modulation. It starts from a lower key, something called A flat major, and it goes to a higher key, B flat, sorry, B major. And this operation is basically equivalent to taking all the frequencies in your first chorus and multiplying all those frequencies by a very weird number, 2 power 1 by 12. Okay, it's like taking all the frequencies in your first chorus. So, if I took my first chorus and suppose I took the Fourier transform of it and I add this kind of form, my second chorus will have the same shape, except that at every point I'll have to spread this out and move it to the right a bit, because whatever was at 100 Hz is now at 100 Hz into 2 power 1 by 12. So whatever was at 100 Hz is now at 100 into 2 power 1 by 12. Why 1 by 12? Because there are 12 notes in the octave. The 12, not notes, but there are 12. If you look from C to C, there are 12 notes on the keyboard, right? Each of those notes are, when you go from one note, C to C sharp to D, you multiply the frequency by 2 power 1 by 12. And that is basically what the song does. The first chorus is, say, at 100. The second chorus is shifted by a multiple of 2 power 1 by 12. And this multiplication of frequency is something which our LTI circuit cannot do. So even if I have this equation, which is your state space model, and which is very fast because I can convolve everything and do everything in parallel, I don't have to compute things in sequence, I still cannot do what I started with. So we have two issues. First, we tried transforms, whatever runs all our charging, but that is ludicrously expensive, it will bankrupt me. Okay. Second thing, we tried state space models, are very RC circuit inspired idea, but that is not even good enough to, like, I cannot theoretically also generate this sort, okay, because it is incapable of doing this modulation. So if you want to model a wider class of frequencies, I need something called, I need nonlinearities in my network. So what I do is, I take this equation and I add a nonlinearity. Xk plus 1 is equal to sigma of Xk plus Bu. Okay? And this thing is what you would call, in regular AI parlance, you would call this a recurrent neural network. You take input X, okay, slight skill issue because of the nomenclature across different fields. In the state space parlance, X is the state of the system and U are the inputs, but in regular RNNs, very commonly X is the input and H is the hidden state. So bear with my flip-flop of nomenclature for just 2 minutes. Basically, you're taking the input, you're going to the hidden state, and based on the hidden state, you're generating the output. And for the next hidden state, you're taking the previous hidden state and the current input, you're updating it to get the current hidden state, and you're giving the output. The next, again, you're taking X2, H1, and you're giving the output. So you're getting, again, in RNN's parlance, this will be HT plus 1 is equal to sigma of W X T plus W X T plus B. Right? You're taking the input vector, you're multiplying it by a matrix W X, and you're taking the previous hidden state. Oh, sorry, I got it. So this is T minus 1, this is T. Yeah, now it's good. Sorry. Yeah, you're taking the previous hidden state, multiplying it by some other matrix WHH, and you're adding a bias term, and the whole thing you're applying a nonlinearity. This nonlinearity could be something like a Lenovo sigmoid or all of that. Okay. Now, question. Yeah, tell me.
Earlier F was there, right, in RNN?
Yes. F, sigma, any function.
Okay.
And just take it. Okay. Now, this form was very useful to us because this recurrent relation, we could put xk, we could put something in xk, and we got that convolution. And the nice thing about convolution is, it is everywhere. It is everywhere in the sense that your phone does a convolution once every 128 milliseconds because everyone now has 5G and 5G requires convolutions to work. Yeah, 5G requires convolutions to work. If you want to know why 5G, like what 5G does and why 5G requires convolutions, come to me after the session. But basically, convolution is something which you can implement very, very nicely using something called a fast Fourier transform. Okay? But if you have this equation, what happens when I put ht minus 1 here? Can you help me write out the equation? So I get ht is equal to sigma of WHH. What is ht minus 1? Sigma of WHH. What comes here? ht minus 2 plus WHX x t minus 1 plus b plus WHX x t plus b. Okay? Can I expand this out of the nonlinearity? No. And I have lost the ability to parallelize and use FFT and use those very fast algorithms. So, okay, now we have 3 problems. Okay, we tried 3 different methods. We tried transformers, which could theoretically do the task but will make me broke. Second, we tried this idea of a linear model. This theoretically also can't do the task, but it's very, very fast. But it can't do the task, so okay, it can't generate music, and I'm sad anyway. And third, you have an RNN, which can theoretically, you can show that this theoretically can model the sequence, but it's slow now, because I have to parse every single state one at a time. And if I have to pass 11,000 inputs, I have to run this 11,000 times. And if you know how gradient descent works, for this you will have to start from the 11,000 input, calculate 10,999, 98, 97, and keep going till you reach 1, and update all those gradients, and you will be here till next year. Well, then that's done. Okay, so you have something that's theoretically can run, and also what happens? You are going to multiply all these 11,000 terms, and 11,000 terms, if it's trained well, your updates are going to be small. So it's going to be 11,000, like what? Floating point, like numbers between 0 and 1. And if you multiply so many numbers between 0 and 1, it's basically going to end up being 0. So you're not going to learn also. You're going to get cooked. So this can theoretically work, but it's extremely slow and it's not going to train in practice that well. You have transformers which can do the task, but it's extremely expensive and make me broke. And you have this thing which can't do the task, but it's very fast. And I am sad, I can't generate the sum. Okay, how do I solve this is the topic for the rest of today's session. Yeah.
Over there, in the case of RC circuit, what are the two functions we are convolving?
Oh, you are convolving the response of, yeah. You are convolving the response of the RC circuit with the input. So, this is the frequency domain representation of what the RC circuit does. Take the time domain of this, whatever that time domain representation would be what you convert. Okay?
What are the UK and HK?
What UK and HK are is, come after the meet, I will tell you. Okay? After this session. So, can anyone summarize the problems that we have here? I introduced three architectures. We introduced a regular transformer, a state space, and a RNN. Okay, what is the issue with the transformer?
Lazy.
Too much investment.
Huh?
O of n square.
O of n square, too expensive. What is the issue with the state space thing?
It does not have non-linearity.
It does not have non-linearities, but the advantage is very fast. What is the third one? RNN. RNN issue is?
Might not even work.
It might not even work. Second, it's sequential. Each sequential, I cannot parallelize this thing.
Like the third one also has the same problem like O of n square now.
No, this is not. This is
Like
O of n only, no. Like if I have 11,000 tokens, I have to just process 11,000.
It's O of n.
It's O of n. Which is still alright. Like O of n is still alright. Like will not make me broke as fast as this. Okay. Anika. Start from okay, it is right there. So again, just for a recap of what our convolution earlier was, we were getting for this equation, we were getting something along the lines of xk plus 1 is equal to k power k x0 plus summation over all I from 0 to k power k minus 1 into v, so k minus I into v into u1, right? Okay, so she'll start from that.
I'll just do it. Okay, yeah, hi everyone, my name is. Okay, so like all this time we saw all the different ways we can use, like different AI architectures you can use to handle sequential data, where there's like a huge number of data points and you have to like remember data points from like lots of steps ago and use it to generate your next like output. So you can have transformers, which is like accuracy wise is the best way, where you compare every single past token to your current token and get the output. And then we have RNN, and then we have SSMs, which is computationally a lot faster. But the thing is, it's too simple. Like it has no non-linearities, and it can't really model and preserve information that well. And then we have RNNs, which they have the non-linearities that you need, but it's difficult to model long-range dependencies. Like context from say like a million data points ago, which you have with like audio signals and all. Like even if it's like 5 minutes of audio, it's gonna have so many like frequencies, and that is gonna be hard to model. So what you want to do is like we'll use the same SSM equation, but you want to find an optimal A matrix that can like that can model. You want to find an optimal A matrix that can model how this hidden state changes. So this is like derived from the linear time invariant differential equations. So this is the change of the hidden state. So this is very important. So what you do is like this is a hidden state of this like SSM. How it changes is represented by A into the like previous hidden state. Plus B into the new input. So I just talked about how current sequence models struggle with long-range dependencies, and you need to find a way to like encode this like input function that you have. Like this is basically all the inputs you had till this point, all the data you had till this point. You want to encode all that history in a less memory intensive way. So to do that, we need what we can do is. So to remember context from millions of steps ago, what you can do is you have this complicated input function that changes with time. What you do is you approximate that input function. Like if I'm not being clear with what like an input function is, like if you have audio, like it just it's gonna like. This is like the input and it varies with time, right? Like so with this time step you've gotten this much data points. The next time step you get more. And it keeps adding. That's the whole point of sequence to sequence models. So what you want is like at this point, if you want the output, you need to remember everything up to this point. And all of this is really complicated and it's memory intensive to store this entire function. So you can't remember everything perfectly. What I'm saying is this input function you can approximate it, like not exactly this, but like a reconstruction or approximation of this. Store that because it requires less memory. And then by getting your output, you take this approximation and reconstruct from that. So yeah, I hope I was clear. Are there any doubts? So like when you think of approximating functions, like what is the first thing you would think of? Like something you've done in JEE or something? Not regression, like a technique that you can write a function in terms of other functions, other simpler functions.
Taylor.
Yes, Taylor series. So yeah, like Taylor series is something we all know. You can approximate a bunch of functions as just like polynomials, as a linear combination of multiple degree polynomials. And like you might think this is not like you can't approximate really complicated functions with this. And that is true, but even if you look at E of x with just 5 like steps with increasing accuracy, you can approximate it like very well, or like really well. And so even with complicated functions like polynomial linear combinations can work quite well. And so now if we look at the format of like a polynomial approximation for a function, you have like a0 into x power 0 and a1 into x and like up to an x power n. And if you kind of just look at the coefficients, it's just like a set of numbers. So essentially what I'm saying is you can represent any function as a linear combination of these polynomials like x power n minus 1 up to x. So all you need to keep track of is these coefficients. And any function, if you have those coefficients, you can just multiply by each polynomial and get the approximation to that function. So this kind of resembles a vector, if you will. Because a vector is just a set of numbers that encodes something in a space, right? So like let's look more into that. So like, do you guys know what vector spaces are? Okay, so like a vector space is essentially just a set of vectors that follow certain additive and scaling properties. So for a vector to belong in a specific space, if you have vector u and v in that space, u plus v must also belong to that space. And if you have a vector u in a vector space, cu, like any scaled version of that vector, should also belong to that space. And if these conditions are satisfied, you can like call those set of vectors a vector space, and you can perform certain operations on them that will work, like linear algebraic operations like dot products, transforms, etc. And all those operations are defined on this being like a vector space. So like why are we talking about vector spaces right now? So we need to talk about something called a basis. So every vector space has something called a basis, and the basis is just n vectors, like if it's an n-dimensional vector space, and we'll just talk about a 2-dimensional vector space for now. So that is like just r squared. Like, so a 2-dimensional vector space, the basis for this is like, does anybody know what the basis for a 2-dimensional vector space is? Yeah, x and y, or like I cap and j cap. So what I'm saying is, any vector in this space can be expressed as a linear combination of I cap and j cap. So it's just going to be a I cap plus b j cap. Yeah, so that's the basis of the vector space. And like as I talked about linear combinations, what we saw was a lot of complicated functions can be a linear combination of simpler functions. So this kind of resembles vector spaces in a way, right? And so let's look at functions and vectors and see if like they are similar and they act similar. So yeah. So for vector addition, what you do is if you have like 2 vectors, you add them element wise, right? Like coordinate wise. So yeah. And for functions also it works the same way. So if you want to get the addition of 2 functions like f of x and g of x, you want to find f plus g of x. What you do is you add the value of the function f of x plus g of x at the same point for the infinite points that it spans. So if you have a function f of x here and g of x here, to find f plus g of x at this point, you can add just f of x at this point plus g of x at this point. And if you keep doing this for every single infinitesimally small, like the spacing is infinitesimally small, if you keep doing this, you will get f plus g of x. So it's kind of like element-wise addition, and it's the same with scaling. So to scale a vector, you scale each of its coordinates, and to scale a function, you scale like each and every single point. So yeah. So you can see how functions and vectors kind of behave similarly, except that here you have finite dimensions, there you have infinite dimensions. You can't really sum them up, you have to integrate them because it's infinite. Okay, so I talked about vector spaces where you have a basis and every other vector can be as a linear combination. The same way, because functions act similar to vectors, we can define something called function spaces. So the function space, so for vector spaces, the base is a vector. So for function space, the basis should be like other functions, right? Like simpler functions. So that is what we talked about in the very beginning. So here, the basis functions of this polynomial function space are like 1, x square, x cube, and all the way up to x power n. And any complicated function like or like e power x, sin x, cos x, you can represent them as a linear combination of these polynomial functions. So sin x, cos x, and all those So these are the basis functions, and those other complicated functions lie in this function space. So yeah. And you have a vector of coefficients of basis functions. So basically any complicated function can be represented as a vector, where the basis is also functions, like not other vectors. Okay. So now that we established that functions space similar to vectors, can we find dot products of functions? Because in all of what we talked about, dot products are very important in measuring similarity between tokens and stuff. So to measure similarity between functions, this is something that seems useful. So can you do dot products of functions? And yeah, that you can. And that is not this exact same, but it's something called the inner product. So for the inner product, let's start from vectors themselves. So
any doubts so far about the idea of using a function space where functions themselves can be the basis? Any doubts? Yes, no? Did you get the feel for why you would treat it that way?
yeah, okay, we were looking at inner products. So to get a dot product between two vectors, let's just start with vectors. What you do is you just sum up the corresponding coordinates, right? So I goes from 1 to whatever dimensions you have. So this is in the finite case. Vectors have you can sum them up like the finite dimensions. You can sum them up one by one. But with function spaces, you have infinite dimensions. So what do you do when you want to sum up infinite numbers? Integrate. That's all. So to get the inner product of f and g, you just integrate them, and you do f of x, g of x. And here we do something called a weighted inner product, where you have a function called a weight function or a measure. And so this is a really interesting thing that we're not going to go into right now because of time and stuff. But what it essentially does is you can use it to manipulate how much weight you want to give to which part of the function. So if you have two functions like f of x and g of x, if you want to give the similarity score a less weight in the past and a more of the weight in the recent past, you can modify the weight function to do that. And also another thing it does is when you have polynomials that are very high degree, the integral can blow up and go to a huge sum, and this weight function helps it to stay finite, the dot product to stay finite. So yeah, and you have some domain over which you and this inner product obeys all the properties that a dot product obeys. So this is a good this is a good way to think of dot products of functions. Okay. So now that we've talked about dot products, what do we do to say that two vectors are completely unrelated?
Dot product is 0.
Yeah, dot product is 0. So to say that two functions in the function space are perpendicular, or essentially they're different directions and they don't encode the same information, you use a property called orthogonality. So to do that, you just set the inner product equal to 0. And this plays an important role in selecting the basis for a function space. Because we looked at 2D basis functions. And the reason why they're so good is because they're perpendicular. So like you can efficiently encode information about every other vector. So in the same way, for a function space, if you choose orthogonal basis functions, you can encode the information of your complicated input function more efficiently. Because like each part of the polynomial is not related to each other. They can capture different directions. Okay. So the most simple basis functions that we saw were 1x, x square, x cube, and like the thing before. So are these orthogonal? So we can just like test it out. So like let's just set like arbitrary domain of like okay, let's just set like an arbitrary domain of 0 to 1, and for simplicity like the weight as 1, and let's do like okay, yeah, minus 2. Sorry. Okay, so yeah, let's do the first polynomial in this is 1 and times x dx. Wait.
What is x dx? Integral x dx from minus 1 to 1.
Let's see.
Yes.
Okay, this example was kind of bad, but let's do the
They're
other.
orthogonal. 1 and x are orthogonal.
1 and x are orthogonal.
Yeah.
Yeah, they are. That's something we should remember. And yeah, 1 and x are orthogonal. That's good. Let's try for x and x square. Oh. That is orthogonal.
X is 1 and x square.
Let's take 1 and x square. So yeah, this is going to be x cubed by 3 minus 1 to plus 1. That's going to give you 2 by 3. It's going to be 1 by 3 minus 1 by 3. So 2 by 3. So like 1 and x square are orthogonal, but 1 and x square aren't. So if we use this set as a basis functions, 1 and x square are going to kind of encode like the same information in some respects. So we want all the vectors to be mutually orthogonal. So this is not the best basis. So these aren't orthogonal. Can we make them orthogonal? So there is a technique to make functions. Yeah. Yes. I mean, if you saw the name, that's fine. But how does it work? Can somebody tell me?
Yeah, what is the technique to make basis orthogonal?
Use one odd power, other even power.
But then, if you use only odd powers, you cannot model x square. Then there is no even function that you can model. But some people are saying gram split. But do you know what gram split is?
It's a way to solve the equation.
We can solve it.
Gram split.
Yes, exactly. So what you can do to make the vectors orthogonal is, like the functions orthogonal, you remove the part of the second function that's parallel to the first one. So they'll both become orthogonal. So let's do that like step by step. So let's keep this domain, minus 1 to 1 and rate of x is 1. And like your first term is going to be like, let's set a few polynomials v that we already have. So v0 is 1, v1 is x, v2 is x squared, and so on. That's the basis that we have right now. And we need to orthogonalize these bases. So let's make an orthogonal set. So u0 is just v0. This is your reference. And to get u1, what we do is take take v1 and then subtract the part of v1 that is parallel to u0. Am I clear? Okay. So yeah, we want to make v1 like totally perpendicular to u0, like a reference thing. So what you do is you take v1 and subtract the projection of V1 on U0, which is essentially just the dot product of here inner product times U0 by the magnitude of U0 vector by magnitude of U0, and I'm using inner products here because we're dealing with functions. So let's do that for the first thing. So here our V1 is x, so U1 is going to be x minus inner product of U0 and V1 is going to be integral. U0 is just 1 into V1x, and weight is just going to be like 1, so dx, and into U0 is like still 1, and this is going to be integral 1 dx from minus 1. Okay. So yeah, so it's just going to be x because integral 1 dx from minus 1 to plus 1 is going to be 0. It's going to be x squared by 2, so 1 by 2 minus 1 by 2. So it's just going to be x. So yeah, as we said, 1 and x are orthogonal. You don't need to do anything to it to make it orthogonal. So yeah, so we have our new orthogonal set. Let's also find it for the next one. So for U2, let's write this down. So we have V2 minus V2 U0 by inner product U0. So is this enough if I just subtract the parallel part with the reference vector? Do I have to do something else?
Question. What do we need U2? Is it dimension of the vector or something?
No, U2 is just we have these basis functions, right? V0, V1, V2. V2 is not inherently orthogonal to all of these. So you want to subtract some part from V2 that's parallel to your reference things to create a new vector which is going to be orthogonal. It doesn't have any parallel part with that. Okay. This is vectors of that.
Everything are functions.
Yeah, they're all functions.
They're all functions. I think your doubt was whether they were the dimension. No, everything is the function.
Yeah. So yeah, they're all functions. And so V2 is x squared. Okay, so is this enough if I just do the dot product with the first dimension? Yeah, I need to do it with U1 as well. Because we need all of them to be mutually perpendicular. So what you do is you V2 U1 by. So we have x squared minus V2 U0 is x squared 1 dx into 1, and this is just going to be integral 1 dx, and minus V2 x squared 1, which is x dx. I hope it's visible. Should I write somewhere else? U1 is again x, and here you do x squared dx minus 1 so here you're going to get x squared minus, so this is going to be x cubed by 3, so you're going to get 2 by 3 divided by integral 1 dx is going to be x from minus 1 to plus 1, so you're going to get 2, and this is going to be x cubed dx, so x power 4 by 4 minus 1 to 1 is going to give you 0. So your third polynomial, I'll write it here, is going to be x squared minus 1 by 3. But one thing that one property that's going to be useful is setting every polynomial, polynomial of 1, f of 1 for each and every one of these functions should be equal to 1. So we'll impose that constraint right now, I'll get to that a little more later. And so to do that, you need to multiply a coefficient with this. So U2 is going to be equal to 3 by 2 into x squared minus 1. Because only then when you substitute 1 over here, you get 2 by 3 and you get U2 of 1 is going to be 1. So we just calculated very simple basis functions as a starting point, and we orthogonalize them. So now we have orthogonal basis functions, and these are gonna encode information in a very efficient way. So now, so this is what we derived. So does this remind you of something? These equations, we calculated P naught, P1 and P2. Do these remind you of anything you studied?
How many of you did PH 1020? 1020. Okay. How many of you did? Yeah, 1020 guys. A should go once. C by 1001. Yeah. 1001. Okay. How many of you? Okay. Yeah. So if you have done both these courses, you have seen it in two separate locations. So this is a question of how well you remember your course.
Okay, anybody who has done quantum chemistry also?
Quantum chemistry, anything related to hydrogen atom, quantum chemistry, anything related to that?
Spherical wave function.
Yes. Yes. You are talking about the spherical harmonics, right? For the hydrogen atoms. How are those related to this? What is the difference?
There's some small modification that you do.
Instead of X, it should be positive.
Exactly. X is not. And wait, you want to wait? You next week asking lots of questions. Let us try to plot it. Let's do X. Let's set as X as positive. And you guys are going to help me plot the function R is equal to mod T of n cos theta. Okay? Fine. What is P0?
One.
Yeah, so what is that going to be? R equal to 1. That is
Spherical coordinates.
R equal to 1 is circle. Right? Anyone confused? No, R is equal to 1, theta is equal to 0. You don't solve that if you have confusion. Yeah. Okay. Let's do this. P of 1. What is P of 1? R equal to cos theta. P of 1, we are putting x equal to cos theta, we are getting right? Can you tell me how it should look? At theta equal to 0, what is the value of the function? 1. At theta equal to 90 degree, what is the value of the function? 0. At theta equal to, I'm doing mod, okay? At theta equal to 180 degree, value of the function is 1. Theta equal to 0, theta to 270, what is the value of the function? 0. Fine. So you're actually getting something like this. Okay? Third, let's do the third one. When does this function go 0? X equal to 1 by root 3. Correct?
Plus minus.
Plus or minus. So cos theta goes as 1 by root 3 once every quadrant, right? So let's draw those two experiments. Okay? At theta equal to 0, what is the value of the function? Theta equal to 0.
1 minus
1. Theta equal to 180, what is the value of the function? 1.
Same one.
Theta equal to 90 degree, value of the function is?
Minus 1 by 2.
So you're taking mod, so 1 by 2. No, 270, 1 by 2. In between is going to go to 0. Okay. What orbital is this? S. This P. This
D.
D z square. Now, does it match? You've seen this before? Right? Yeah.
Bro, there was modulus is there, not
Yeah.
So how did it affect?
And this is sharp. I mean, like, this continuous. So, how you're getting the orbitals themselves is you have to rotate this. This is just projection onto one plane. The orbitals are 3D, so you have to spin this. That is why dz square we remember in all your visualization as this donut shape, right? The donut shape is how you take this and rotate this around, you get a donut. Yeah? Makes sense? Okay.
So yeah, this is just like Desmos, like I just put those functions. And yeah, so we started with basic polynomials, then we orthogonalized them to get some other like polynomials which are like unrelated. And these can model some really cool physical phenomena. So like they happen to model the hydrogen atom orbitals, and there's also something in physics, like can anybody remember?
Chemistry. I also told you would have seen this in page 1020.
Okay, it's the multiple expansion. So each like polynomial is going to give you a higher like pole expansion. So the first one is just going to be a monopole, and then it's going to be dipole, quadrupole, octupole, and so the like legendary polynomials that we got by orthogonalizing those basic ones can model like dipoles and like cool charge distributions. So yeah, so these we can like rely on them to kind of give us good representations of complicated functions. So where we started was we wanted to model like input functions that change in like weird ways over time and store the history of that function in an efficient way. So we looked at approximating functions. So we thought of using polynomials as the basis functions and doing linear combinations of those polynomials to approximate the function. And we need to choose the best polynomials for that. So we want to do orthogonal polynomials. And this set of orthogonal polynomials, like these aren't the only types of orthogonal polynomials, you have other types like larger polynomials and more. So this is a good way. So let's try out like approximating your input function using legendary polynomials. So that is what an architecture called, or not like a math thing called HiPPO does. So HiPPO stands for higher order polynomial projections. So you just take like your history function, if you will, like u of t represents the input that you keep adding to your sequence to sequence model, and that varies like this. So what you do is at each time step you try to reconstruct it using your legendary polynomials, and you note down the coefficients of those polynomials. So you have the polynomials, you need like we are talking about the coefficient vector, and this thing changes as you add more of the input. Because when you add more of the input, you can change the approximation to fit it better. So what HiPPO does is it maps your input function to your like coefficients of the approximation. Okay, so the coefficient vector encodes the history of the input in the best possible way, and this gets updated with each time step. So in this time step, you get more of the signal, so you approximate it to fit the rest of the signal as well. And these represent a state of the system. Okay. So what we want to do is model the state dynamics and see how they change. So you just take the derivative of that, and like this follows a normal linear time invariant ordinary differential equation. So x dash of t, like how your coefficients change, is going to be some A matrix into the coefficients plus B into the input at that point. And how you find the output is you take your hidden state, like your approximated function, and you reconstruct it to get the output. So, and this t into ut is just like it's like something you call a skip connection. So, like this is the input, and what you want to figure out is what you add to the input. You don't really have to worry about that. So, what extra you add to the input to get the output. So, this is the most important thing. And the matrices A and P are called HiPPO matrices, and they determine how the hidden state changes. And that is what we need to figure out. So to like get the HiPPO matrices, well, I hope I'm clear that the x that you want to find is the coefficients of those orthogonal polynomials. So you want to model how these coefficients change as you add more and more of the input, or with each time step. And yeah. So approximating functions using orthogonal polynomials. So this is what we've been talking about. It's the function, which is your history function. It's a linear combination of orthogonal legendary polynomials. So it's going to be some coefficient to the first polynomial, P0, then another coefficient into P1, other coefficient into P2, and you add all of them. And our job is to figure out what these coefficients are and keep track of them as a hidden state. So to figure out these coefficients, let's just like try something out. So the function, like the approximation is going to be summation Ci into, like let's just say Cn into Pn of x, and n goes from 0 to like whatever, to however much you want to approximate it, and yeah, so this is there, and let's just to start with, let's try the function, like taking the inner product of the function with like some pj, like some polynomial, and what you get is, it's going to be f of x is going to be summation c I pi, just keep it like this, into pj, and this is going to be summation ci into dot inner product of pi pj, because inner products follow linearity, and you can take them inside the sum. And so what is special thing about pi pj? For orthogonal polynomials is the basic definition. Yes, it's 0 whenever I and j are like not equal. So pi pj is gonna be 0 when I is not equal to j, and it's going to be some lambda when I is equal to j. And this is orthogonal polynomials. For orthonormal polynomials, this is going to be 1. So they're scaled so that when you multiply the same, like take the inner product of pi, you're going to get 1. And so yeah. So let's say these are orthonormal. So what happens is you will get Cj, because everywhere where I is not j, you're going to get 0. So all those coefficients get cancelled. So yeah, if you take the inner product of f and pj, like your input function, and the j polynomial, like j Legendre polynomial, you get the coefficient for that polynomial. So that's pretty cool, right? So you now have a way to find these coefficients, which is all you wanted from like the beginning. So, and now if you want to find the like derivative of those coefficients, you just take the inner product, so which is f into n Legendre polynomial into the weight dx, you integrate it and you differentiate it. So all this math is like very complex, but you can solve it using certain recursive properties of Legendre polynomials. So these Legendre polynomials are by nature have some recursive properties where you can relate like the derivative of the nth polynomial to the like value of the n minus 1 polynomial. So we're not going to go into that. If you do want the math, I can like send over resources. So once you do all this, you will get an expression that looks like this, which can be summarized in this way. So the derivative of the coefficient vector is going to be n minus n plus 1 by t into the actual coefficient vector itself, plus this form. So it's going to be 2n plus 1 into 1 by 2 power 1 by 2 into 2k plus 1 power 1 by 2 cket, and k is going to vary like. So this Cn is going to be the nth the coefficient of the nth polynomial, k, like, and it's going to go from n minus 1, n minus 2, and all the way up to 0. And yeah, so what we wanted to do all this time is to model the coefficient in this manner, right? Like x dash or c dash is equal to ax plus b2. So it's just f over here, which u and f are like the same thing. And so if you compare this with that, you can find a matrix which basically gets you this, like this equation, but in matrix form, because CD vector is going to have like Cn, Cn minus 1, Cn minus 2, Cn minus 3, like all up to C naught. So to essentially do this multiplication, but in matrix form, you like A matrix can be this. So it's going to be 2n plus 1 power 1 by 2, 2k plus 1 power 1 by 2, when n is greater than k. So if you want to like visualize the matrix a little bit, like So you have n1 and 2, or like n is going to go from 1, 2, 3 to n. K is going to go from n minus 1 to 0. So yeah, so it's going to be like a matrix where when n is greater than k, you have like some values here. When n is less than k, it's going to all be completely 0. And when n is equal to k, it's going to be just n plus 1. So it's going to be like 1, 2, 3, 4, 5, 6 in this diagonal. And here you're going to have 2n plus 1 power 1 by 2, 2k plus 1 power 1 by 2. So that is the HiPPO matrix. So this essentially gets you like the approximation of your input function in terms of like a linear combination of Legendre polynomials. And you keep updating those coefficients as you get more of the input. So it essentially stores the history in a less memory intensive form, and this HiPPO matrix is the essential operator that you use to get that. So it's just a visualization of what exactly the HiPPO operator does. So this is your input signal, and this is like x of t, where each of these x's represents one of the coefficients. So this is the lowest order coefficient, which is C0, and C1, C2, and C3. So they are kind of representations of this function, but like they're less memory intensive. So this is a cool way in which you can like encode the history of your function and like keep track of it to generate outputs. So this is what HiPPO is, and I would like hand over to Ishita. Thank you.
Okay, so now we'll be discussing one of the state space models called S4, and we'll kind of build on top of what Anika said, HiPPO matrices, but we'll come a little bit later first, just to kind of motivate why we should even study S4 and what's the relevance. This is basically a benchmark called long range arena. So this is as of 2022, and these are the popular models at the time, and S4 is the one we'll be discussing. So these are kind of scores given on each of these individual benchmarks, and these are all like classification tasks. So this is list operations, this is retrieval. So basically, it'll ask a question like, is this data present in some chunk of text, and you just have to answer like yes or no, a binary label. So ignoring all of this, I think this is what we should focus on for now. So what X means is the model does not perform better than a random baseline, which is just getting a score of 0.5. So all of the models up until S4 was introduced was just random answers like 0.5 accuracy. And then when S4 came in, it got 88.10 accuracy, which is like a good almost 30 points higher than the rest of them. And you can see the average scores as well. For S4 is like more than 20 points than the rest of the models. So this is why we should be studying S4. And basically what PathX benchmark evaluates is, I'm given a long sequence and I have to see if there exists a path between 2 points. So if I'm given an image and there are 2 points with a circle connecting those 2 points, is there, like you ask the LLM, is there a path? And it has to say either yes or no. So that's what PathX evaluates. And these are called long range arenas because they're primarily suited for evaluating tasks that require models to model long range dependencies. So yeah, most of these models actually, you'll see that when you're training them, it starts from some random initialization of weights, but S4 is different in the sense that we looked at A, B, C, and D matrices, right? So in that, B, C, D are learnable, but A has a special like form that is initialized with from the get-go, and you don't train A basically. So that's where it gets its computational efficiency from. So I will just rewrite this on the board because it's easier to make that.
Yeah, that's right.
Okay, so these are the two governing equations of almost every state space model that exists. And basically, if you were just to look at this equation without using any kind of special structure on any of the matrices, the computational complexity ends up becoming O of n square L, where n is what I'm going to be taking as the dimension of the hidden space and hidden state vectors, and L is going to be sequence length. So throughout the discussion, this is the notation I'm using. And it also is O of n times L in space because we have to store the XD matrix for every single matrix, because you have a different XD for each token position, and n is the dimension. So this is just another way to look at the same equation. You have addition operator here, you have x dot, which is the same as x dash, and you're integrating it, you get x. So u times d plus a times x will give you, c times x will give you y, and b times u and a times x dash, a times x will give you x dash. So it's the same thing, just in a different format. So this graph was also there on the previous presentation slides, but this top part wasn't there. We were just dealing with the first equation. So this is just continuous time input, and what I'm doing is, with the help of the first equation, axt plus but, I'm getting a hidden state vector which is of 4 dimensions in this case, because we have 4 dimensions. And then I'm taking the second equation and using this 4-dimensional vector to get the output vector, including the skip connection. So basically, this D can be just omitted, and we'll just think of it as a skip connection directly from the input to the output. You're just directly adding the input to Y. So that can be modeled easy, and we'll just be ignoring it for most of the derivations. So yeah, the nice thing about state space models is that these equations have 3 different representations. The one that I've written on the board is the continuous time representation, and this is not really used because we're working with computers. So what we often do is we discretize it and we get the recurrent representation, and then we look at convolutional representation. Okay, let's derive this.
Use the top one.
No, I need this to be visible.
Yeah, so use the top one.
Okay, so say I have a point Tn and a point Tn plus 1, and I have some curve between these 2 points, and I want to find the area here. So one way to approximate this area is to just treat this as some trapezoid, and if this point is f of Tn, and this point is f of Tn plus 1, by trapezoidal rule, what is this area? Can anyone tell me?
T8 plus 1 minus
This one plus slightly representative.
So
I will divide by
this side? Okay. So now if I were to take this function f to be x dash or x dot, can I write this as x n plus 1 minus x n? Because it's the integral of x dash. Works? So if I write it as this, I just get this equal to this thing over here. And basically what I'm going to do now is substitute from this equation. So these things become x dash of tn plus 1 and x dash of tn. And my x dash can come from here, I'll just substitute this back into here. So I'm going to write this as delta. So I get delta by 2 times a into xn plus b into 12 plus a into xn plus 1 plus b into n plus 1. my delta is very small. And because I'm taking the same thing, I'll just take it as un plus 1, and this 2 will get cancelled because I'll get 2 of these. So I just get delta E into un plus 1. Make sense? Okay. Then I'll just take the inverse of this and get it to this side. And essentially, this after taking this inverse, I will get my A bar over here and my new B bar over here. So this is the matrices we get after discretizing this equation. And A will become, or A bar will become I minus A delta by 2 inverse times I plus A delta by 2. And B bar will be I minus A delta by 2 inverse delta B. And C will just remain C, but then just call it C bar. Okay. So I'll just ignore D, like I said, because it's just a strict connection. You'll see them in a lot of models and transformers as well. So what A is called is the state matrix because it controls the hidden state X. And B is called the control matrix. It controls how much of the input we want to be hidden state to be influenced by. C is the output matrix and B is the command matrix. Okay, so let's draw a comparison between RNNs and this discrete time SSM equation that we have.
Yeah, so basically the difference between what we did earlier and what we did now is the kind of discretization. We discretized in one way earlier. I just very naively took f of t plus delta minus f of t whole divided by delta. Here you want to find the same thing, you want to find the area under the curve, but you're approximating the area under the curve as the area under a trapezoid that approximates the curve.
So basically we did rectangular rule before,
Yeah.
now we're doing trapezoid.
In some sense, yeah. Make sense?
Okay, so you would have seen these 4 equations when we were discussing RNNs. If I were to just club the first 2 equations and write h of t is tan h of t plus w h of t minus 1 plus mu x and y cap of t as soft max C plus D H of T. So these two are non-linearities, right? Say I just dropped them, I ignore them, they're not there. So do you see the similarity between these 2 equations after dropping the non-linearities and this discretized equation of everyone? Xk is basically ht, uk is basically xt, and y is the same. Right? And these C and D, don't let this confuse you. These are basically just, this is an affine transform. I could have easily just put just a column of 1s in my H or X and model B and C using that. So yeah, those are just, can be modeled by H and X, either of them. Yeah, so now let's look at the convolutional representation. So, let me just take my initial x to be 0, x minus 1. So I get x naught by discrete time representation as b bar times u naught, and this is my first input. Then I get x1 as b bar u naught plus b bar u1, and so on. I get xk as sigma a power k minus 1 bar b bar u minus I, sorry, not 1. And I runs from 0 to k. Does this make sense? I just recursively put the equation into itself over and over to get the relation at some kth step. Our k will be n minus 1 because our sequence length is n, and we started from 0. And once I have this, I can just put it into yk, and I get yk to be c bar a power k minus I b bar to I. So I'm going to take this whole thing and call it as some kernel k bar. So that is essentially the operation we get. K bar times our convolution will do. And this is a convolution because this is I over here and this is k minus I. So you can think of it as two rows sliding over each other, and this is like the flipped version of the row and this is the row. So I'm doing every single operation that gives me a sum of k. So in that way it's a convolution. So this is the convolution representation. So now that we have the governing equations of state space models, how this would fit into a larger model was if I were to just stack layers of them on top of each other with some normalization or some linearity. So most models just follow this structure. And this is basically the place where most of the differentiation between models comes. In transformers, it's MLP and attention. In RNNs, we saw these equations. These equations. And next steps, we just saw the discrete time equations. And one motivating example is the example of the moving average. So if you see over here, you have 1 minus a and a as the coefficient. So you can think of these matrices in this case to just be one-dimensional, 1 plus 1. And basically 1 minus a is what governs how much of the past we want to remember, and a governs how much of the input we want to influence our current state with. So a is usually like 2 by n plus 1, where n is the number of data we have, but that's just a convention. So yeah, you can see that this equation models exponential moving average, which also proves that R model S4 can model exponential moving averages. But the problem is that the naive application of these equations won't work because, again, the problem of computation complexity comes up. We have O of n square L and we have O of NL for time and space respectively. And these are N and L, as I defined before. So we need to introduce some kind of structure into A to kind of exploit the lower bound of these computation complexities, which is O of n plus L. So we want to go from O of n square L to O of n plus L. And the way we can do that is to think of A having some special structure. So that's what we wanted to model long-range dependencies like the HiPPO matrix does. We want it to we want to be able to apply some kind of special algorithms to A to compute things efficiently and solve the computational challenges. So that's what S4 does. So yeah. Before that, let's just take like a small detour. The issue over here is when we're doing this computation, you can see that we're raising A to some power constantly. And these are going to be big powers if our sequence is long, if our L is large. So the problem of computing the power over and over comes up. So does anyone know what similarity transform is or conjugation? Okay. So basically, if I were to turn my matrices A, B, and C into B inverse A, B inverse B, and CB, this would be a similarity transform. And this B is basically diagonalizing A in one case, if it is diagonalizing.
Did everyone catch what happened there? No? Do you know that some matrices you can write as a diagonal matrix? Only the diagonal elements are non-zero, rest all are zero?
This is essentially that.
Like singular already
Yes.
But now this is, if it's a square matrix, then it's just regular spectral theorem diagonalization, right?
But in general, this is a similarity transform irrespective of what V is, whether I'm diagonalizing it or not.
Got it? You have V and V prime, which you are taking, sorry, V and V inverse, you're multiplying it from both sides, such that A is, if it's diagonalizable, it will be a diagonal matrix. And if it's diagonal matrix, okay, you can continue. Why?
Yeah. Okay, so this is no different than just taking my x and rotating it or changing the basis of x, because this is what my equations become. I get V inverse x is equal to V x squared plus inverse b u, and my x is going to be bx squared. So basically I'm just rotating my basis into another basis. It's not going to change anything. So I can essentially to the essence of b inverse ab is the same thing as a. We're just doing it to exploit the nature of b inverse ab for algorithms that we'll be looking at. Yeah, so the issue with this is we want our matrix to be well conditioned. By well conditioned, I mean when it's raised to powers or when it's inverted, I don't want extremely large values or extremely small values. I want it to be stable. So if I want it to be stable, this v also needs to be well conditioned. And it turns out that for HiPPO matrices, this v, ij entries are actually I plus j, c, I minus v. So if I were to take v 3i comma I, I would get entries of the form like upper bounded by 2 power 4n by 3. And this is a really big number if my n is large. So I need v to be well conditioned, and my best case scenario is for it to be just having eigenvalues equal to 1, because my condition number is going to be the largest eigenvalue by the smallest eigenvalue. And if I want the norms to be preserved and I just want my x to be rotated, all the eigenvalues need to be either plus or minus 1, and that gives me which kind of matrix? Okay, it gives me a unitary matrix. So do you guys know
what the unitary matrix is? No.
Okay, so do you guys know what normal matrices are? A transpose A is A transpose. Yeah, so unitary is basically normal, but this A transpose A becomes I. So A transpose is the same as A inverse, so unitary matrices. Make sense?
A equals A transpose.
Huh?
A equals
A inverse is A transpose for unitary matrices. Because I'm getting A transpose A is I. Okay? Yeah. So what that helps us doing is, one, it preserves the norms, and two, is just a rotation, which is what we want. We want to rotate our basis. But the issue is, HiPPO matrices are not normal. They're actually normal plus some low rank matrix. Do you guys know what a low rank matrix is? Okay, so if I had like if I had an n cross 1 vector, say P, and I had it P transpose, the rank of this matrix is still going to be rank 1. So low rank matrices are basically, you guys know what rank is?
after you do Gaussian what's the number?
Yeah.
Wait, how many of you are from first year? Yeah.
You guys should still know what rank is.
No, you did your second course, right? Wait, no, you're doing series of interests now?
We do
Not now. So, yeah, you haven't done.
Okay, you can just think of it as the number of independent or orthogonal columns or rows, I guess.
Okay, let's
orthogonal.
take detail. Let's actually do it. You want to do it or you do it? Yeah.
If you have a system of equations, the number of
Okay, let's just very
The number of linearly independent rows or columns.
Let's do it very fast. Ultra fast. Rank. So you want this the whole time, right?
Yeah, just keep that running.
This one? I'll read it. Okay, situation is very easy. Scene is you have your matrix. Okay? For simple purposes, I will take a matrix that looks very nice. Okay? Fine. 1 0 0 0 1 0 0 0 0. Okay? And I will multiply it with the vector x1, x2, x3. And I want to find what kind of vectors I can get by this multiplication. Okay, that's the scenario. So, can you guys all see that if I do my matrix multiplication, I get x1, x2, x3, x1, x2, x3, x1, x2, x3. Right? So, this whole thing I can rewrite as x1 into 1 0 0 plus x2 into 0 1 0 plus x3 into 0 0 0. What does this mean? X3 cannot do anything, right? And that also means that since I don't have a 1 in any of the bases, in my B vector, B1, B2, B3, I can never get a non-zero value. Okay? So I have two dimensions that I can use, and one dimension, even though this is a 3 cross 3 matrix, one dimension is kind of useless. Okay? So those two useful dimensions, so I would say this matrix has a rank to it. Okay? Now you can define a rank for non-square matrices. Okay? You can define a rank for non-square matrices. Scenario is the same. I take it like this, and I again take x1 and x2. Right? I don't need x3 anymore. I'm not taking it. So this is x1 1 0 0 plus x2 0 1 0. Right? This is a 2 cross 3 dimension, 2 cross 3 dimensional matrix. Again, you have only two bases that are useful. Here you can never get a non-zero value. So again, for a matrix A that belonging to P cross M, if P is less than M, at max you can have rank P, because you can have only P useful bases. Right? There many are going to be useless because some scenario like this will happen. Right? And how do you find the rank of the matrix? You do some operations to make whatever matrix you have into this form. Okay? Again, for an example, let us take something. Let's do some very simple example. Suppose I have a matrix of this 1 0 0, 0.2, 0.8, 0, 0.4, 0.2, 0.8. Okay? Now, how do I find the rank of this? I take the first row and I want to make it as close to an identity as possible. Okay, that's my goal. I take the first row, I multiply it to 0.2 and subtract. What do I get? Can you tell me what I get? I'm just doing one transfer. I'm not putting equal to, I'm putting one transfer. I'm multiplying first row into 0.2, subtracting 0. What do I get? 0.2 will go 0 here, 0.6. Okay, this will become 0.6.
0.8 itself. Why will that change?
Oh, sorry, my bad. Loss. This is just 0.8. Okay, and here it is 0.4, 0.2, 0.8. Okay, now what I will do is I'll do the same operation here. I'll take the first row, multiply into 0.4 and subtract. Then I'll take the second row, divide by 4 and subtract. Okay, and tell me what I get. 1 0 0. Nothing is happening to the second row. And here I am getting 0. Here I am multiplying this, dividing this by 4 and subtracting. So I am getting 0. And here nothing happens, so this is 0. Okay. And now I have how many useful rows? 3 useful rows. The rank of the matrix is 3. Okay. This is a very hand-wavy, intuitive way of rank, but it works enough for
Where did the 0.4 go?
Oh, I am multiplying first row into 0. I'm doing RR. Like I mean, I'm finding RR. Okay, fine. This is my very quick introduction on that.
So basically, now that we know what rank is, the HiPPO matrix is going to be a normal matrix plus a low rank matrix. And a low rank matrix I'm just going to form by taking an n cross 1 dimensional vector and finding P times P transpose. Does that make sense? So this P transpose is only going to have rank 1 because it came from rank 1. Rank 1 vector, sorry. So how are we going to solve the problem of computing very high powers of A? We're not going to compute high powers of A. We're going to exploit this algorithm called generating function. So instead of computing powers, the generative function is going to make us compute inverse instead. And we're going to only compute one inverse per x at some t or per token. So yeah, the equations so this is going to be, for now let's just treat A as a diagonal plus low rank matrix. I know HiPPO matrix is normal plus low rank, but we'll get to that in a bit based on the stuff that we did over here, similarity transforms. So this generating function basically what it's going to do is I have to compute sigma c bar power k times a power I bar times z, where z is the nth roots of unity. So I is running from 0 to infinity. It is given that when you start to infinity, this result becomes c bar star and I minus b bar z inverse b bar. So the summation of all these powers of a just evaluates to one inverse. This is based on the generating function. So if I were to sum until L instead of infinity, because my sequence length is L, I would get C bar star times I minus A bar L times CL into I minus A bar Z whole inverse times D bar. So because I'm evaluating this, so Z is my unknown variable, and I'm going to evaluate this at the Lth roots of unity. So because I have Lth roots of unity, this E bar L is going to go to 1, right? So this will just be some numerator. This is the numerator. This whole thing. And this inverse is basically going to be our denominator. So how do we evaluate the inverse efficiently?
Before we get to that, why are we finding the generating function?
So we're finding the generating function because we want to go from the time domain to the frequency domain, because we don't want to calculate these high powers. So we're going to do that using Fourier transform.
Any doubt? People, did you get this? This is non-trivial, like a bunch of non-trivial stuff. So you should have that. Any doubt? Yeah. Oh, so again, can you explain generating? Can you write out the generating function?
That is
No, as a sum.
Where is the generating function used? In which algorithm?
That is of course algorithm to go from the computation of these powers to that.
So the problem still is that you still don't want to calculate the very high power of A. You want to be very smart about it. So you define the function.
So basically what the generating function is doing is, instead of computing power, we're going to compute inverses. So the map between power computation to inverse computation over there is basically what the generating function is.
Like inverse is also expensive, but since the power that you're multiplying K is so big, inverse is relatively much cheaper. So you want to trade off doing one inverse instead of doing a million matrix multiplications. Okay, that's the scene. So you cook up a generating function. If you look at the generating function, you take the nth derivative of the generating function, you will get the nth term in that sequence. Okay. I will leave it to you to figure that out, or I will show
We
it to you
can
after.
share resources.
Yeah. But basically, you are trading off doing a million matrix multiplications for doing a single inverse, which is a huge save. Nice. Yeah.
So, like we said, computing the inverse is also expensive, especially if you don't have some really nice structure to A. We just have, for now, we just have diagonal plus low rank. Diagonal matrix inversion is very easy, right? How do you invert a diagonal matrix? Just do 1 by the diagonal entries, right? But A is not diagonal. We have diagonal plus low rank. So there's this algorithm called the Woodbury identity, which says that if you're inverting a diagonal plus low rank matrix, the answer is also going to be a diagonal plus low rank matrix. And the structure of that is going to be like this. So my A is diagonal plus or minus, let's just say plus for now, P star. And the star is the same thing as transpose. I'm just writing it as star because it's conjugate transpose. We're going to deal with real values anyway, but just for general. So I get this. The symbol is the diagonal matrix, right? or based on the low rank matrix. So this you can see is like pretty easy to compute, almost as easy as it is to compute just the diagonal matrix itself. It's just a bunch of matrix multiplication after rank. So now we've gone from diagonal to diagonal plus low rank, but I mentioned that HiPPO is normal plus low rank. So how do we go now from diagonal plus low rank to normal plus low rank? So remember we discussed over here that this is a similarity transform, right? So essentially, if I do a similarity transform on my A, B, and C, that's the same as going. If I were to just do spectral decomposition, I would just get the diagonal versions of A, and I would rotate places. Essentially, the same thing to the scale-based model. Doesn't make a difference. We just get slightly different equations at the end, which is this. So yeah, this is the same as those equations that were over there, but now that we've diagonalized it, it just turns into these two equations on the screen. So yeah, that's it. Oh yeah. So we're not going to prove like why this is true. Over here, B is backside, again L is sequence length, is N is dimension of X. So this is the computational complexity of all these models and for all these parts of model naming. So we have parameters, range, space, parallel, and inference. So parallel just means this is parallelizable. We know that RNNs are not parallelizable. We know computation is basically the same thing as S4. You guys will probably learn about computation a little later, but yeah. So this is just some statistics for why S4 exists and like what did it bring to the table. So you can see that all the ones in bold are the best complexities we can get, and you can see S4s are all of them are bold. So they outperform the rest of the models significantly in speed and computation complexity. Any doubts?
Any doubts? Yeah, any doubts? We'll come back and give big picture. So we want to come up with an AI model that can generate the song that we wanted, right? That's where we wanted to go. Transformer, very expensive, will make me broke. RNN sequential, I cannot train. So let's just try our hope using this linear business. Even though we need to somehow cook up how to get non-linearities. We will figure how that comes. But even if we have to do this linear business, we have to compute one very expensive step, which is a power k, a power a million. Now a power a million, instead of doing a power a million, now we just need to do 1 inverse. So we have reduced time complexity a lot, right? We have gone from doing a very big matrix multiplication a million times to just doing 1 inverse, which is very nice. Now the next point is to actually bring back the non-linearity so that I can actually generate the sum. Okay. Yeah. So we had before, now we have
okay. So like we saw SSMs, all the math behind SSMs, but one thing that they struggle with is language modeling. So in language modeling, a model needs to be able to do is recalling tokens from a while back and comparing tokens to see how related they are to each other. And this is not something SSMs can inherently do, but attention can do this. So this is a very important thing about attention that makes it so good at modeling languages. And but then it's too expensive, like we saw. And SSMs with calculations, especially with like smart calculations like we saw before, they can be very efficient. So let's try to find a way in which SSMs can be used to SSMs can be made better to do recall tasks and token comparison tasks and almost mimic attention. So that is what the H3 layer is. So that H3 stands for hungry hippos. So this is the main algorithm for that. So it looks a little complicated, but I'll break it down. So what you first do is you have your input, your history, the input function. And as you get the input, what you do is you to that to get the key values from that. WQ will get the Q values, and WV to get the V values. So you get the queries, keys, and values from the input. Like you just transform them, and we saw that yesterday in attention. And once you get those query key value matrices from your U, what you do is you take the keys and you perform a shift SSM on it. So what a shift SSM does is it just as you add a new input to that SSM, it will update the vector to forget the last one and add the new one. So it just kind of shifts it up as you add new vectors. So at each point you will remember the last m tokens. So when you add a new token, it will forget the first token from your window, then add the new token, and as you add another token, it will keep sliding basically over the entire sequence. So that's what SSM shift does. So it maintains kind of like a memory record the last m tokens in your sequence, and slide over. So for the first 10, 1 to 10, then you go to the 11, then 3 to 12, like that. And then what you do is you just, this is less expensive than the actual attention mechanism, because you don't have to keep track of every key and get every key value product. So you just keep track of the last m keys, and then you multiply that with the values to get the local interaction. So the value of your current token, you multiply the last m tokens to get the local interactions. So that's what SSM shift of k into v does. So this is kind of not perfect, because you're just doing it over windows, right? So you're forgetting information from before as you move across the window. So to solve that, you have SSM diagonal. So we saw that what SSMs do is they can remember information in an efficient way, as you keep going. So what this does is you keep sliding over the windows, right? So SSM diagonal keeps track of all the information of the past k windows. So as you slide, you have SSM tracking all of that from behind. So SSM diagonal remembers the state over the entire sequence, while SSM shift keeps shifting. So it keeps forgetting some tokens, but this SSM diagonal will make a record of those tokens which get forgotten. And after this, you have the query matrix. So what you do is you have all this encoded information in the history. So you want the relevant information for your query right now. So you just do a dot product to get those interactions. So this models interactions over the entire sequence, while the inner multiplication just models local interactions. So in this way, you can basically compare tokens and recall tokens using just SSMs instead of attention and soft maps attention. So yeah, this was the H3 layers, and each the SM diagonal uses a HiPPO matrix for its initialization, because it needs to keep track of the history. So both SSMs are the hungry HiPPO 1 and hungry HiPPO 2. That's why it's called hungry HiPPO. So this is something that you need to know to understand the next architecture that we're going to do. So I'll end there.
Okay, so now I will be covering the Mamba architecture. So Mamba at its time of release was hailed as a potential competitor to transformers because of its scaling properties, computational efficiency, and also its performances on context-based reasoning tasks. And in this portion, we will also be discussing that how this particular architecture differs from the prior architectures we have covered, like RNNs, transformers, and structured services models, and all the things we have discussed so far. Yeah, so as I said that one architecture isn't enough. The thing is that various sequence-to-sequence models which we have studied so far, they come with certain trade-offs. If you take example of RNNs, they at the time of inference they have a constant complexity. At the time of training, they operate in a linear fashion. So the problem with RNNs, however, is that it can't, let's say, model long sequences because of the vanishing gradient problem that occurs. Also, the recurrent operations can't be parallelized in sequence. So that's why we had to move on to some other architecture, and then we came across transformers. Transformers use a mechanism called attention, in which each token attends to every other token in the sequence, and through which we get the contextual embeddings, rich contextual embeddings, and they keep a track of all the embeddings which we have. And the problem with attention again is, even though it is effective on natural language processing tasks like machine translation and sentiment analysis, but it is expensive, as it was shown prior in the session. So we have to do something to overcome that. Then we came up on structured state space models. Structured state space models, they solve the issue of RNN of capturing long-range dependencies, but again also they can be operated in parallel like the attention mechanism in transformers. But when it comes to producing results as effective as transformers, they fail in certain aspects in certain tasks, which we will be discussing through an example. Yeah. So the main problem with S4, or the main task which it fails on, is the induction edge task, which has been described in the research paper of Mamba as well. That what is the problem with S4 and why we need a new state of SSM. So I will be explaining what this induction edge task is. To give a brief overview of this task, basically induction heads are specialized attention heads which emerge in multi-layer transformers, and it is crucial for in-context learning. By in-context learning, I mean that model should be effectively able to recognize patterns in a sequence, and based on that pattern, it should be able to predict the next token which is coming up in the sequence. Like whenever you type something on chat, it is automatically giving you the next word of the next sequence as you go forward. So SSMs, why they can't do this, that also I will be explaining. But let us start with the example of this induction edge task first. So let's say I have a pattern of can anyone guess what will be why with this pattern? Any answers? C. Okay, let's see how transformers, how the induction edge decide what will be the next token or the next alphabet in this sequence. So let's say I have this particular letter A. I will write this sequence one more time. Now this is your current token, and using that you have to predict the next one. So you check how many times B has appeared after A and how many times C has appeared after A. So when you match it, you can observe that so you can see that out of 3 cases, B has appeared 2 times. So probability of Y being B is 2/3, and probability of Y being C is 1/3. So most likely, according to how induction edge function, the likely output should be B because it has a higher probability. And why transformers are able to do this? Because in attention mechanism, each and every token is able to attend to the previous tokens. So as a result of in-context learning, you can observe that since it has attended to each and every token, it can recognize the patterns. It can see that when A had come before, what came next to it. So this is called as prefix matching. So when A came and it saw that B had come twice and C had come twice, so it assigns a higher probability to B of appearing on the next token. So that is called prefix matching. And once it matches the prefix, then the second step is copying that particular token and placing it on the vice position. So that is called copying task. So transformers can do this efficiently because of the attention mechanism. But in case of SSMs or the prior architecture which we have studied, they carry information in some hidden state. So if I take example of SSMs, you can see that this particular information is carried in a hidden state. So when you give the explicit token information, you can't use that and directly extract the previous token. So that is the reason why these models fail on this induction head tasks, because they don't get the explicit token information. They are just carrying the summary with themselves, and due to this summary, they don't have information of what came before. So this is one of the tasks where the SSMs fail and transformers perform well. But again, the problem here is that you still can't make it more memory efficient, because still you are computing so many tokens and storing them in your memory, which is making the which is making the space complexity of the order n squared. So we still have to overcome this, and to overcome this, we have proposed a new state of architecture, which is selective SSMs. So how selective SSMs work is, they make these parameters of SSMs A and B dependent on your input. So by making them dependent on input, you give the higher priority to a certain token which should appear next in the sequence. What do I mean by this? Here you saw that B has a higher likelihood of appearing on this position, whereas C has a lesser likelihood. But when you have these SSMs, they assign equal probability or equal likelihood to each and every token, which is making them fail on the induction hedge task. So that is the core reason which we have solved right now. And what we want to do is, we want to make this parameters of SSMs dependent on your input. So that is what we will be seeing, that how we can do this. And once we make these parameters of SSMs dependent on input, there arises one more problem. That is, now you can't use the convolutional operations, because convolutions work when there is no shift invariance. Now since your parameter change depending on the input, so you have to model this recurrently. You can't use those convolutional operations here, because your A and B both are changing depending on the input. So we will see how we will solve this particular thing. There is an algorithm called parallel scan algorithm, which we will be discussing in detail afterwards. So what conclusion we came to is that first of all, the SSMs which we have studied, those can't model, those can't produce effective results on certain tasks which transformers can do effectively. So we decided to make them dependent on the input, and by making them dependent on input, we came up with some another problem, that is, how do we do these operations in parallel. So that we will be discussing how we can do that. So as I said, the parameters B, C and delta, these are made dependent on your input, so that whichever token is more important, it gets a higher likelihood of appearing next into the sequence. And A we have kept as it is, because A is essentially dependent on this discretization parameter, and since this parameter is already changing, there makes no sense to change this A as well. So these three parameters we will be changing. Like this X is basically the linear projection. Linear projection is basically the weights times input plus the bias. Similarly with C, and broadcast is basically repeated linear operations on different inputs. And this is the discretization parameter, which is a soft plus. Soft plus is an activation function which is used to keep this term positive, because this is like time difference between the occasion. So we want to keep it positive, so that's why we have used the soft plus function. And the choice of these parameters are basically similar to how the gating mechanism works. So to give a brief overview of what gating mechanism is, gating mechanism is basically how much you want your information to go forward and which part of the previous information you want to ignore. So that is what gating mechanism does. Here also we are doing the same thing, that what part of the information should have more likelihood we are sending it forward, and which doesn't have that much likelihood or that much priority of appearing, we are keeping it on the backward side of it. So this is what we came up with. Also, since we have made our parameters dependent on the input, it adds an extra dimension because your sequence length will be changing for every interval. So this leads to another problem. As I said, now you were first operating in these two dimensions. Now you have these three extra things, which is increasing the complexity of your algorithm. So we need to solve that as well. Also, in case of S4, your training is convoluted, that is the training which you do is in parallel, but when you come to inference you use recurrent mechanism. Here you can use only recurrent mechanism, which can be optimized, can be done in parallel using a scan algorithm, which we will be discussing later. Yeah. So talking about mechanics of selective SSMs, that how basically you incorporate this selection mechanism. That is how you decide on which token should be passed further and which should not be passed further. That is modeled through this mechanics of selective SSMs. So let's understand the gating mechanism, which I told before, that what information should be allowed and kept behind. So we take for simplicity the N, A, B. N is taken as 1, A is taken as -1 and B is taken as 1. We keep this H delta parameter as linear function of x and linear projection of x, and this tau delta as the softness function. And when you substitute these values, you basically get the same thing, just A and B are different here. So when you look at this equation, this is called a leaky integrator equation. But what I mean by this is that you can see that this is actually ds by dt. Here there should be one dot also, so yeah, there should be ds by dt there. So you can see that it is something like you are forgetting your hidden state and you are adding some input. So it is like remembering, it is a standard model for remembering whatever sequence you have. So you are forgetting some of your past inputs and adding something new. So that is what this equation is describing. And these are the derivation steps. You can look through it. It is basically a gating mechanism. If you guys get an idea of gating, then it will be easily solvable. But let's look at the final result itself for now. The final result you can see is that you get a function which is sigmoid of linear projection of xt. Now what do I mean by this is, linear projection is basically the weight times input plus the bias matrix. So you learn those weights during the training, and using those weights you control how much of your input should be passed on to the next hidden state. So this is called as the gating mechanism. You are deciding which particular input should have higher priority of going forward and which particular hidden state you have to forget, so that the most important information you are not missing and the information which is not required for your task, you are avoiding it and you are letting it be behind. So this is how the selection mechanism is incorporated in SSMs. Yeah. So as I said that since these are recurrent operations, you can't do it in parallel as we saw in RNNs. But the researchers came up with a scan algorithm, and it is very similar to prefix sum operation that if you guys have done some programming, then you might be aware of this particular problem. So in prefix sum, you have an initial array, and the prefix sum array is basically the first element of the initial array is kept as it is, and then you add the first and second element to get the second element of the prefix sum array, and then you keep on adding these two things to get the third element. Then this to get the next element and so on. So this is the prefix sum operation, which you can do using a simple for loop operation, and this is having linear time complexity. How you can relate this with SSM model is, let's say these are your model inputs x0, x1, x2, x3, x4, x5, and these are the hidden states in the prefix sum array. So this h1 will be basically like a bar times this plus b bar times this will give you h1. And similarly, you can compute all these things. So these operations you can see are computed in a recurrent way in a linear fashion. But there is a way of making these operations done in parallel. So the thing is, as long as you follow the rule of associativity, basically what does this rule say? That even if your operations, your order of operations doesn't matter, but unless and until you are getting the same results by not doing those orders, you still can compute these things in parallel, and that is done through a concept called GPU threading. And here is the example of how this works in the GPUs. So this is like a 6-dimensional array, but this particular example is for a 16-dimensional array. You can see that the first 2 elements are computed here itself, but some elements are calculated at a later stage also. So as I said, doesn't matter the order of operations, as long as you are getting the right results, accurate results, you can still do it in parallel. And what is the advantage of this? You can see that time complexity, which was before O of n, now gets reduced to O of n by t, where t is the number of parallel threads. And as the sequence length is increasing, you will require more and more threads. So you can even more optimize this particular operation and do it in parallel. So that is one of the advantages and one of the algorithms which researchers came upon. So now what are things we have? We incorporated the selection mechanism, the selective SSMs which use selection mechanism. We have incorporated that. Now basically we have made our SSM parameters dependent on the input. Dependent on input means that you can assign higher weights to the information which is important, and you can discard the information which is not useful for you in the further stages. And also now you have made this algorithm even faster because you use the scan algorithm, which helps to reduce the computational inefficiency. And this is the architecture. Like once you have understood this particular selective SSM block, that how it works. Now you can incorporate the Mamba architecture. It is basically combining the design architectures of the H3, that is the hungry epoch, which was covered just now, and the gated NLP block of the transformers. So you have an input matrix. You use a projection layer to increase its dimensions. You increase its dimensions so you get better feature separation and better representation. So you use this particular thing. Then you use convolutional operations so that you can capture local features. And after that you have an activation function which you send to the selective SSM block. Selective SSM block, as I said, it models, it uses that parallel scan algorithm, and also it is making your SSM parameters dependent on the input. So that is incorporated in this SSM block. And you have another skip connection. So this basically is all the hidden state information which is coming, and this is operating at a particular time step. So this is for a particular time step, and this is combining all your previous time steps. So when you do element-wise multiplication, you retain the information which you want to pass through your Mamba block. And this Mamba block is not a single block; it is similar to transformers. It has it has many such stacked blocks, which then you apply another linear projection so that this input dimension and this input dimension is same, and you send it to the next Mamba block. So this is the architecture and all those things which I have explained. So as I said, in case of induction hedge task, which was this particular task where you have to predict the next token in the sequence, it has given almost, not almost, it has given 100% accuracy even on increasing sequence length. So this is something to look for. Also in case of selective copying task, so there are two types of copying tasks, that is the standard copying task and a selective copying task. Standard copying task is pretty simple, that because you have a fixed space between each and every token. So that can be done using RNNs, SSMs, and any other model as well. But when it comes to selective copying, let's say if I have a paragraph of 500 words and I tell you to give only the proper nouns. So the difference between the tokens would be varying. It could be that the proper noun occurs after 3 tokens or 5 tokens or 10 tokens. So for that, what you need to do is you need to store a selective information in your memory so that you can accurately capture which token is required for your task. So even on that task, if you consider, if you don't use selection mechanism, then you achieve 56.4% accuracy. But when you incorporate selection mechanism in the Mamba architecture, you achieve 99.8 accuracy. So that is really fascinating here. Also, you can see this is the graph for floating point operations. This is basically the measure of computations, and this is the perplexity. Perplexity is basically the uncertainty of predicting the next token. So you can see even as the computations or number of operations increase, Mamba has the lowest perplexity out of all of them. Means low perplexity means that it is more certain to predict the next token compared to all the other architectures. So this is also one of the things. And these two graphs are basically similar, but this is for different types of sequencing. And the dataset used is the Pi dataset, which is an open source English language dataset, which is a benchmark dataset for all these evaluation tasks. Even talking about the language modeling, which is one of the most important domains, you can see that Mamba with increasing parameters, the perplexity also decreases, which means it is having more certainty to predict a particular token or sequence of tokens. It outperforms various models like HiPPO is a transformative based model, and all those models it has outperformed. And even on some science based question tasks, it has provided better accuracies than other models, and also the common sense reasoning tasks. Yeah, this is one of the most important things which we were looking forward to. So this scan algorithm, which I discussed before these slides. So this scan algorithm, you can see as the sequence length increases, the time taken to get the desired output. You can see it is the lowest for the algorithm which we are using. So it is the lowest, and it outperforms flash attention also, which is one of the best scan algorithms used in different architectures. And also,
just to point it out for sure, everyone sees it. This is logarithmic scale, right? So this is say around 10. This is around 1000. It's 100 times faster. Okay.
Yeah, so it is really fast, and you can see even the inference throughput. Inference throughput is basically number of tokens it can process per unit time. Mamba, even with more number of parameters, outperforms some of the transformer architecture as well. Let's say we take this particular example. You can see with 6.9 billion parameters, it outperforms the one with 1.3 billion. So that is also really phenomenal. Finally, this is the most important thing, that how our selection mechanism actually worked out. You can see that if we make our parameters selective, if we make all the parameters selective, we get the lowest perplexity. Again, back to induction head task, you can see that it is able to recognize patterns and select which or predict what will be the next token in the sequence. So these are the model applications. You can see how it is helping. And yeah, that is pretty much it.
So, yeah, finally, I get to have a model that I can generate my song without going broke, because of all the optimizations you saw today. You would have seen so many optimizations in 3 years, and you added non-linearities, and you made the system time dependent. So yeah, you can now train Mamba to generate music and do it in a much more efficient way than training a big transformer.
We have a sample code for that.